Okay, let me explain our plan. Before Christmas, we took our derivatives and we used them to get shapes of curves. And we had, to help us, a large number of definitions and theorems, such as the sine of f prime theorem, Fermat's theorem, blah, blah, blah. And those theorems, definitions and theorems, are the ones that you are to be using on your project. How many of you have gotten started on your project already? None of you? Okay. You might want to make sure you get started on that. It's due Friday. You probably can't do it all Thursday night. So, shapes of curves are what you need to be using, definitions and theorems are what you need to be using for your project. Now, in addition, we're going to do some other stuff with derivatives. All this month, we're going to be doing applications of derivatives. So in particular, we're going to have uses for tangent lines. That's this week. One idea, that's it. One big idea that we're going to do all this week. And then we're going to take a look at finding absolute maxes and mins. And some theorems related to absolute maxes and mins, like the mean value theorem. And then we are also going to take a look at related rates. And all of these are different applications of the derivative of the firm. So that is our plan for January, maybe the first week of February, depending upon how it goes. And then once we get done with that, then we're going to jump into integration, a whole different concept, a related concept. Now, what's that? Well, that's the thing I want to talk about. On the 13th, which is the Friday before exam week. So January the 13th, we're going to have a test on all of the application of derivative stuff that we've done so far. That's going to take us up through here, right?
So it includes what we did before?
Yes, it does. We're going to have a test on all the bracketed material. If snow happens, and snow does happen sometimes, and we get pushed back, then I will give that test on the exam period. Just be an old test, it won't be a full exam length test. It'll just be a long test. And there will be. But if our schedule continues and we make it safely through without having any wonderful snow days, then you don't have to come in. Yay. So I put you in the unusual position of hoping for no snow. Good. Any other questions? Okay, fantastic. Let's talk about tangent lines. This whole week we have one big idea, and that is a tangent line approximates a function. Say this again because it is the crucial big idea. A tangent line approximates a function at the point of tangency. Let's make this specific and precise by using precise math language, and then we're going to see how powerful this idea is. Here is the precise math language. If f prime of c exists, then f of x is approximately equal to tangent line expression that we know and love, f of c plus f prime of c times x minus c for x close to c. Now, as we did with the limits, I'm not going to define the term close. We do that in Calc 2. But I think you all can reasonably understand close means close. So this is our one big idea. Now, to see what this means, first of all, let's go back and practice doing some tangent line construction. Suppose f of x equals the square root of x. Construct the line tangent to the graph of f of x at x equals 4. Notice that the word construct is math language for create the equation of. So you guys do that, and I'm going to pause this. So if you're following along at home, you go ahead and create your tangent line as well. Okay, so hopefully you have a point and a slope. And the point that we're talking about is the point 4, 2, that is c, f of c. And the slope that we're talking about is 1/4, that is f prime of c. Notice that the slope is not 1/2 root x. It is 1/2 root 4, right? Because we're talking about f prime of c, not f prime of x. And so when I write the equation for the line tangent, what I get is y is equal to 2 plus a fourth of x minus 4. And here I just took the point slope form and I added 2 to both sides. Now I could simplify this if I wanted to. I noticed that Tony did that on his, and there's nothing wrong with that. But this is a nice form for observing some things that are to come. Okay? So that's my tangent line. Now, here's how we apply this. This is amazingly powerful. Suppose I pulled you in off the street and I asked you, what is the square root of 4.1? Okay? In other words, I'm asking you, give me the number that when I square it, I get 4.1. The positive number that when I square it, I get 4.1. My guess is that you probably would go, it's kind of close to 2, right? And that's about it. Tangent lines enable us to give a pretty good answer without working too hard. Watch this. Is 4.1 close to 4? Yeah, 4.1 is close to 4. Since 4.1 is close to 4, now, because of that fact, I can use my big idea for the day, the tangent line estimation theorem, and I can say that the square root of 4.1 is approximately equal to the tangent line evaluated at 4.1. What am I doing here? Let's look at a picture. Here is the graph of y equals square root of x. And what I did was to create for myself a tangent line at the point x equals 4. That is tangent at the point of tangency x equals 4. And if you take a look at the tangent line values, which are in black, and the curve values, which are in red, you can see that in a neighborhood of 4, for x is close to 4, you can't tell the difference between the y values on the line and the y values on the curve. They are approximately the same. And so what that means is that I can estimate the square root of 4.1, the red value on the curve, by getting the black value on the tangent line instead. And that's easy. I can do that without a calculator. 2 plus a fourth of 0.1, or 2 plus 0.025. And without ever having to do any fancy math at all, the only thing I had to do was to construct a tangent line and plug in. I get an estimate for the square root of 4.1. How good is that estimate? Okay, well, let's pull off the math. Get your calculators out and compute the square root of 4.1. How do we do? That's really good. We're good to within 2 parts out of 10,000. Wow. Wow. That is an amazingly good estimate considering that we didn't have to work very hard. I'm impressed already with the tangent line estimation. There is a bonus feature about our tangent line estimation. Once I have created a tangent line, and in our case, that tangent line is at the point of tangency x equals 4, then I can use that tangent line estimation for any value of x that is close to 4. In other words, I can recycle it. I only have to compute the tangent line estimation one time, and then I can recycle that for as many values as I need for x is equal to 4. So if you ask me, what is the square root of 4.06? Then I could say that that is approximately equal to 2 plus a quarter of 4.06 minus 4, which is 2 plus a quarter of 0.06, which is equal to 2 plus, let's see here, that would be 0.015. And we get 2.015. What's the actual square root?
2.0149.
In other words, basically correct within 4 decimal places. And I didn't have to work hard at all. All I needed was a single tangent line estimate.
So which point am I using?
Ah, great question. How do you choose a point? Excellent. So here's the whole process if we're going to do a tangent line estimation. Let's take a problem and do it fresh. Let's estimate the square root of 8.8. Okay? Square root of 8. Now, we're going to start by identifying a function. What function are we talking about? What function? The square root of x. Sure. We're trying to find a value for the function square root of x. Now, here's where we get to Jennifer's question. We're going to let c be a value that is close to 8.8 that we know how to deal with, that we know the square root of. Do you know a value of x that is close to 8.8 that we know the square root of? 9. Yeah, exactly. So we're going to let c equal 9. If there were some other value of x that were closer that you knew the square root of, you'd pick that. So we're going to let c equal 9 and construct the tangent line. Go ahead and do that. Construct the tangent line. If you're following along at home, construct the tangent line also. So you should have point 9.3 and slope of 0.6. So that y is equal to 3 plus a 6 of x minus 9. Everybody good with that? And now, we can say that the square root of 8.8 is approximately equal to y of 8.8. This is a good way to write that, which is 3 plus a 6 of now negative 0.2, which is going to be 3 minus 0.0333, or 2.9667. So the obvious question is, how do we do? That's not bad. That's not bad at all. You're very impressed with the quality, with the precision, really, of that estimate. And you didn't even have to work very hard. Now, I've done this for square root functions, but we can literally do this for any function whatsoever as long as the derivative exists at the given point. So, if we use this procedure on a completely different function, for example, estimate e to the 0.15 power. Ugh. If I pulled you off the street and said, here, do this, estimate e to the 0.15 power, you'd be like, how do I even? That's like the 100th root of e to the 15th power. No, not going to do that. Or tangent line estimate. What's our function? E to the x. What's a good c? 0, because I know the value of e to the 0 and the derivative there. So we have point 0, 1, and slope. Since f prime is equal to e to the x, f prime of 0 is equal to e to the 0, which is also equal to 1. And I can very quickly create my tangent line y equals 1 plus 1 times x minus 0, or just 1 plus x. This is an interesting tangent line. Of course, what it's saying is that here comes my curve y equals e to the x, and here comes the line y equals 1 plus x. And what I'm saying is that for x's that are close to 0, then 1 plus x is close enough to e to the x to provide an estimate of the value of e to the 0.15. Specifically, y at 0.15 is equal to 1 plus 0.15 or 1.15. And that's it. That really hard computation that we were going to have to do, e to the 15th power and take the 100th root of that, don't have to do any of that. All I have to do is this. And I have to understand that this is not the exact value, it's an estimate. What is the true retail value?
1.161.
1.161. Okay. That's still pretty good. It's 1 part out of 115, so that's less than 1% error. Okay. Now, a couple of different directions we can go here. But one that's interesting to us is, what can we say about the quality of our estimates? In other words, this is not exactly the same as this. So what can I say about the quality of the estimates? Now, here I can find the actual value just by plugging into the calculator. But I can't always do that, right? In particular, if all that I know is a value for f and for f prime without knowing what the equation for f of x is, then I can create a tangent line estimate, but I can't say anything more about how good this estimate is. If I want to evaluate the quality of my estimate, then there are 3 things that I can do. The best, the gold standard, if I can do it, is to simply say that the error is equal to the difference, the absolute value of the difference between the estimate and the true value. If I can, I will evaluate the quality of my estimate like this. But this is actually rarely possible to do, and the reason for it is really simple. If I knew the true value, I wouldn't bother to estimate. right? So this is rarely possible, but it's the best way to go, if you can. The second best thing that we could do is to put a bound on it. In other words, we could say that the error is going to be less than or equal to some bound, which is a function of x. This is the kind of thing that you learn to do in a numerical analysis class. We're not going to do that here, because the computations can be kind of hard. But this is something to look forward to in college. The third thing that we can do, and it's easy to do, is that we can determine whether our estimate is an overestimate or an underestimate. By an overestimate, what I mean is that my estimated value is too high. Or in other words, that the value that I got from the tangent line y is bigger than the actual value f of x. And the other possibility is that y could be an underestimate. Third possibility is it could be just right. And that doesn't happen very, very often, but it does sometimes happen. Now, how can I tell if y is an overestimate or underestimate? If I don't have the actual value of f of x, you might think it would be possible to do, but actually I can look at the shape of the curve. Take a look at these two different scenarios. Consider, first of all, a scenario in which my tangent line is above my curve. If the tangent line is above my curve, then that means that my curve's rate of change decreases away from a constant rate of change. In other words, my curve is concave down. It will always be the case that y will be an overestimate if f double prime is negative for all of the c's for all of the x's between the point of tangency and the point of evaluation. Now, this is not an if and only if. This is only an if thing. If it so happens that my curve is concave down, then I know that my tangent line is an overestimate. We had that situation with our square root curves, our square root estimates. If you go back and look at the square root estimates that we had, because the curve y equals square root of x is a concave down curve, take a look. We got 2.025, the actual was less than. When we estimated the square root of 8.8, we got 2.9667, the actual was a little bit less than. And that happened because the curve was concave down, so that the tangent line was above the curve. On the other hand, if f double prime is positive on the entire interval, including the point of tangency and the point of evaluation, then y will be an underestimate. And you can again draw a picture to see why this is true. Here comes my tangent line, here comes my curve, and my curve increases faster than my tangent line. To do that, its derivative has to be increasing. The curve has to be concave up. And we saw this happen when we estimated e to the 0.15. We got 1.15, the actual was larger. Why? Because the curve y equals e to the x is concave up, and therefore it lies above its tangent line. So we can evaluate the quality of our tangent line estimates in a rough way simply by taking a look at the sign of F double prime on the entire interval from C to X. Now, if the sign changes, we're not going to be able to get any information, right? But if the sign is constant on that whole interval, then we can say something.
So we were just saying that as an overestimate, underestimate.
Yeah. Yep. And there's a little bit of value in that, right? So you would like, if you're planning for a party and you're figuring out costs, you would like for those costs to be an overestimate. How are we doing? Okay. Well, let's consider a scenario that often shows up. And that is that we have an unknown function. Well, we have a function known at one point only. Let's say that we know that f of 2 is equal to 5, f prime of 2 is equal to, how about 6? From this information alone, estimate f of 2.5. Go. So hopefully you have a tangent line. We would say that f of x is approximately equal to the tangent line f of 2 plus f prime of 2 times x minus 2, which is 1.5 plus 0.6 times x minus 2. This is, oops, we want to keep our approximately equal sign because we understand that these guys are different. But I can freely substitute one for the other as an approximation for x's close to 2. This came up in the other class. Is 2.5 close to 2? Huh. An interesting question, isn't it? Next year, when you take Calc 2, either here or in college, you're going to quantify that question with epsilon and numbers. But for our purposes, we're going to say that close is something that you recognize, and we're also going to say this. Close is on a sliding scale. The further away you get from 2, the worse your estimate will probably be. Or at least the worse it could potentially be. So now having done this, we would say that f of 2.5 is approximately equal to 1.5, 0.6, 2.5 minus 2, which simplifies to 1.8. Is that what you guys all got? Okay, good. So let's take and ask this question. What information would I need to know in order to know whether this is an overestimate or an underestimate?
Concavity.
I would need to know concavity. In other words, I would need to know the sign of that double prime. Where would I need to know it?
X equals
Stronger.
2.5.
Stronger. I actually need to know it for all of the x's between 2 and 2.5. So that if, for example, if f double prime were known to be positive on the entire interval, don't really have to include, probably could include 2 to 2.5, then I would know that, draw a quick tangent line, tell yourself what's going on, but the tangent line estimate is an underestimate. That is to say that the true value of f of 2.5 is definitely bigger than 1.8. a little bit of terminology that you're gonna see in your book. A lot of people, and I'm one of them sometimes, will call the tangent line estimate, let's try that again. Y equals f of c plus f prime of c times x minus c. We've been calling this the tangent line. A lot of people will call this the local linearization of f of x at x equals c. Let's unpack those words and see what they mean. Local linearization. First of all, the linearization means to turn into a straight line. In other words, what I'm saying is that for x's close to c, our point of tangency, I am going to pretend that f of x is a straight line, even though it's not. I'm going to linearize f of x. And the only thing that's required is that f has to have a derivative at x equals c. But it is also local because it means that it is only valid in a neighborhood close to c. If I take an x that is way far away, for example, in our example that we have here, if I were to take x equals 6, which is nowhere close to 2, then the f of x estimate that I would get right here, which would be 0.664, 2.4, 3.9, would be probably very far off from the true value of f of 6. The tangent line is a good estimate, but only in the neighborhood of the point of tangency. It is a local linearization. Does that make sense? So you'll see that terminology, local linearization, used a whole lot in your textbook. What was the other thing that I wanted to say about this? Overestimate, underestimate, sign of f double prime, good. All of that. I see it. Go ahead.
How did you get that double prime? Or how did you see that?
No, I just said if we happen to know. Yeah. We were not given that particular information. We would have to be given that in order to communicate. Uh-huh. Jennifer, did you have a question?
No,
Okay.
I'm just curious, like, how you got that.
Yeah, double prime. Yeah, that has to be additional added information. There's no way, given only these two pieces of information right here, that you can infer anything at all about a double prime. Okay? Cool. We're going to call it a day. I will see you tomorrow, and we're going to have a second, completely different use for tangent lines.